Hello class, welcome to Geometry Lesson 5.1. So we're going to talk about perpendicular and angle bisectors. So our questions today, what is the relationship between a segment and the points on its perpendicular bisector? What is the relationship between an angle and the points on its bisector? So we want to be able to use perpendicular and angle bisectors to solve problems. So before we get started, it's useful to define the perpendicular bisector, especially because we're going to be using it in the next couple of examples. So a perpendicular bisector is a line, segment, or ray that is perpendicular or intersects to form right angles to a segment and intersects the segment at its midpoint. So for example, in this example, if we were to have two arrows here, then this would indicate a line, right? So let's assume that our perpendicular bisector is a line, like as it is in this diagram with my arrows here. And the segment and let's assume that this is my line segment here. And we'll call it line segment AB. And so if you look at this example, you can see that this is cutting this line segment AB in half. And so notice that this from A, let's call this point C. So we know that AC is the same measure as CB. And you have this right angle here, and that indicates that it's perpendicular. And so hence why it's called the perpendicular bisector. So in this case, this line right here that's cutting the other segment in half is called the perpendicular bisector. And remember this short-term symbol for perpendicular is this upside down capital T.
All right, so what we're going to attempt to do today is we're going to investigate a special theorem involving perpendicular bisectors. So we have in front of us is a line segment xy, and the measure of this line segment, the length of it is 4 inches. Okay, we know it's 4 inches, and what we want to do is we want to divide this so that it's 2 inches on each side, and we want to cut this at a 90-degree angle. So in order to do this, we're going to use a compass, put one point in the compass on X, and you're going to extend you're going to change the distance of this compass so that it's a little bit more than half of the line segment, like such. And then we're going to draw an arc above the line segment and below, and you're going to repeat that, maintaining the same distance on the other side. Okay, so now you should have two arcs. We're going to mark the points where the arcs cross and above and below. Next, we're going to connect the 2 points here in a straight line. Okay, so we have here a line. We got a line segment xy, but we have a line here because it extends forever in both directions. We'll call this line L. All right, so this line L is what we refer to as a perpendicular bisector. Perpendicular meaning that it crosses this line segment at a 90-degree angle, and it crosses at a right angle, and it also cuts this in half. Bi meaning two, sect meaning cut, as in section. So it cuts this into two congruent segments. So now if you measure this out, since we knew that this whole thing is 4 inches, each side should be 2 inches. And that's exactly what it is. That side is 2 inches. This side is 2 inches. And notice we did this without using a ruler, right? All I did was I drew a line segment. Of course, I measured the line segment, but that's only to show you that it's the same on both sides. But regardless, you don't even have to measure this line segment. If you used just a compass using this method, then it'll always work out that you'll cut it in half. Now, and we can also measure this 90-degree angle. So we know that this is a 90-degree angle. If I use a compass, I'm going to line this up with the middle here. This lines up here, this lines up, and notice it lines up at the 90-degree angle, so I know that this is a 90-degree angle here based off of the protractor. Okay, so this theorem that we're going to discuss. So if you are traveling on this perpendicular bisector, if you're a point located somewhere on this bisector, let's say you're located here on this perpendicular bisector. And if you wanted to travel to x or travel to y, well, it should be the same distance, right? Because you're in the middle, you clearly cut this in half. And so if you were to travel from here to here, let's say this is a city. You're here, you want to travel to city x or to city y. Well, that should be the same distance, right? And we can actually show this. So let's go ahead and draw a straight line here. And we'll draw our two alternate paths to those two cities. And so we know that this should be the same distance as this, right? And we can actually measure this just to be on the safe side. So if I measure this, this is about 2 1/8 inches. So 2 1/8 inches, that's 2.125 inches. Same here, 2.125 inches. So 2 1/8 inches. And so it doesn't matter if I'm anywhere on this bisector, I will travel the same distance if I were to go to x as I would if I were to go from here to y. And we can show this with another example. So let's say I'm over here instead. I'm in point, we'll call this point P. Let's call this point Q. And then let's call this R. Let's say I'm in point R, a bit farther away. And again, I want to do the same thing. I want to see if that distance is the same. Okay, so if I measure that distance now, and that's about 2.5 inches. Looking at that, right? That's about 2.5 inches. If I go here, again, 2.5 inches. So it's the same thing. So what we established here is no matter where you are in this perpendicular bisector, the distance from city X to or city Y, or any of those points, from any of those endpoints, is going to be the same from wherever you're located on this bisector. So this theorem right here is known as the perpendicular bisector theorem. And so if I know that xq is congruent to qy, and I know that this angle is a 90-degree angle, this angle is a 90-degree angle, then I know that any point on that bisector will be such that this distance px is the same as this distance py. And that is the perpendicular bisector theorem. And this is important because now I know that since these distances are the same, this classifies this triangle as an isosceles triangle. We know isosceles triangles have two of the sides the same measure, and they have very special properties. And I know that if I cut this here, it's going to cut this into two identical and congruent right triangles. And so I know by SSS, because I know that this is the same measure as this, so I got S. I know that this is the same measure as this, that's another side. And I know that this is the same by the reflexive property as this side on this other triangle, right? Since they're the same triangle, they share that side. So by SSS, I know that this left triangle is the same as this right triangle. So there's a lot of cool things that you can get from this symmetry.
All right, so now that we kind of investigated this perpendicular bisector theorem, let's go ahead and present it formally. So if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So this word equidistant right here, that just means the same distance. So this means that it's the same distance. Okay, so when you see equidistant, it just means that it's saying that any point on this perpendicular bisector, which in this case we're talking about point P, is equidistant from both endpoints. Both endpoints here are x and y. And so it's the same distance from P to the endpoint x as it is from P to the endpoint y, or they're equidistant. And so therefore, Px is equal to Py. And this is the perpendicular bisector theorem in a nutshell. All right, so let's look at an example in which we prove the perpendicular bisector theorem. So let's actually go ahead and prove this. So we're given that L is the perpendicular bisector of xy, of line segment xy, and we want to prove that Px equals Py. So let's use a two-column chart. So remember, we're going to start with the given. So L is the perpendicular bisector of xy. Next, what we want to do is we know that because it's a perpendicular bisector, then that means I know that this, by definition, this has to cut through the midpoint of this line segment. And so therefore, I know that this point right here, which we ended up calling N, or actually it should actually say Q here, not N. So because we called Q the midpoint here, and so we said that Q has to be the midpoint of XY, and that's because that's the definition of perpendicular bisector. It's going to cut through the midpoint of the segment, and it's going to cut it in half, right? And so, and also we know that the angles have to be right angles because it's perpendicular by definition. All right, so because we know it has to be perpendicular and has to cut through the midpoint, we also know that by the definition of the midpoint that these two line segments are the same, and so we say that xq is congruent to qy. Then moving on to the next side, we know that by the reflexive property of congruence, we know that this side is congruent to itself. And so therefore we basically can use it, we can basically classify this as another side that's congruent to both triangles, right? And so I'll just mark that with 2 check marks because they both share that side. And then we know that the angles PQX and PQY, which we know are congruent, which we know they're congruent because they're both right angles, right? As we mentioned earlier, since they're both right angles, they're both equal to 90 degrees. And so therefore, they have to be congruent to each other because all right angles are congruent. And so now, because we know that this side is the same, we have a side, we have an angle, and a side. And so we know that these two triangles are congruent by side, angle, side. And then we know that PX, because those two triangles are congruent, that also means that this side of this triangle, which corresponds to PY, those have to be congruent as well. By the congruent parts of congruent triangles are congruent, CPCTC. And then now that we know that those are congruent, then we know that these two segments have to be equal. So that means PX is equal to PY, and that's by definition of congruence.
All right, so now we're going to investigate the opposite, sort of like the opposite scenario of what we covered earlier. So earlier we covered that basically that if this distance was the same as this distance, if from x to, let's say, q was the same distance as from q to y, then we were trying to show that px, this distance from p to x, is the same as the distance from p to y. And so now, this time, we're going to start with the assumption that we know that this is congruent. So we know that this here, the distance from p to x, is the same as from p to y. And let's verify that that's the case. Of course, we want to verify, we want to investigate this. Okay, so if we were to measure that, that's almost 3 inches, right? So it's 2 3/4, and here it's here. Let's double check that measurement. I want to make sure it's actually a little bit more. This is 3/4 right here, so it's actually Yeah, so it's actually 2 7/8. So it's actually pretty close. So, and then this here is 2 7/8. So they're the same measurement. So that means, so this is about 2.875 inches. It's about 2.875 inches, if I did that math correctly. So 2 7/8. And so we know that those are the same. We're starting with the assumption that those are the same. Now, if that is the same, if it is the same distance from from x as it is from y, then that must mean that this distance is the same as well. That's what we're trying to figure out. Okay, well, and then this also means that this point P is on a line that would cut this in half, and not only cut this in half, but meet this at a right angle. And that's what we're trying to say. That's what we're trying to conclude from this observation. If we know that this is the same, then that must mean that this is on a bisector, which means that this bisector, this line here, if you were to call this an imaginary line, if you will, is a line that will cut this at a 90-degree angle, and this is a 90-degree angle. We can measure that with the protractor like we did last time, and that these distances are the same, right? That's a question mark, but we know that if we investigate further, then that's 2.5 inches, that's 2.5 inches. So we know that those are the same, and so this must be true that this is identical, which means that this is a bisector, and we know that that's a 90-degree angle. Now, let's look to see. So now we know that this is true. This is the converse of what we just did. This is called the converse of the perpendicular bisector theorem. Converse means the reverse. So we're essentially reversing the theorem that we talked about last time. Now, let's look at point R. Clearly, point R doesn't look like it's the same distance from x as it is from y, right? If we were to draw this, or if we were to measure that, well, that's about, so looking at that, this is 2 5/8 inches from here to here. And then if we measure from here to here, well, that's over 2 5/8. That's a little over 3. So that's 3 1/8 of an inch. So clearly, the distances here are not the same, which means if distances aren't the same, that's going to mess up this measurement. If this were to be a 90-degree angle, right, then that's going to mess up this measurement as well. Okay, so we can see that there's a relationship between those things. Now, what if we instead had this going at this angle? Well, now that's going to cut this in half, right? That's going to cut this because clearly it's at the midpoint, because it looks like it's going to cut this in half. We can investigate. We can see that it's going to cut this in half at that point, right? At this point here. But this is no longer going to be a 90-degree angle. This is going to be greater than a 90-degree angle, right? So if we were to measure this angle, then this is going to be at the 0, and this right here is right around here. So it's a little bit over 100 degrees. If you can see that, that's about the 100 mark. So it's a little over 100 degrees. Or a little bit before 100 degrees, I guess. Let me double check that. Yeah, it's about 100 degrees on here. So it's definitely not 90 degrees here, right? So therefore, it's not perpendicular. So even though this cuts it at the midpoint at an angle, it's not perpendicular. So it's not a perpendicular bisector. And in addition, this distance is not the same as this distance, right? We just said that. So the only way for this to work is if P is in the perpendicular bisector for this to work. All right, and so that's what we're looking at for the converse of the perpendicular bisector theorem.
All right, so now that we've demonstrated or investigated the converse of the perpendicular bisector theorem, we want to go ahead and just kind of formalize it. So we have, according to the theorem, if a point is equidistant from the endpoints of a segment, so therefore, it's the same distance here, which is why they mark it with the tick mark here. So basically these two distances are equidistant. Then it is on the perpendicular bisector of the segment. Okay, so it's saying if those are equidistant, then that means that this line L has to be a perpendicular bisector, which means that it has to be a 90-degree angle to both these. And that means that this is cutting this in half, which means that xq is equal to qy, which is what it says here. All right, so let's go ahead and prove the converse of the perpendicular bisector theorem. So again, we're given that these distances are the same. We're given that px is equal to py. How can we prove that L is the perpendicular bisector of xy? All right, so we'll do it with a two-column chart. So we know that px is equal to py because that's given in the problem. And now we know that the triangle pxy is an isosceles triangle. How do we know that? Well, because that's what it means to be an isosceles triangle. That's the definition of an isosceles triangle, is when you have two of the sides the same. So we know it's isosceles. And so therefore, by the isosceles triangle theorem, that means that this angle pxy is congruent to this angle pyx. Now that we know that, what we're going to do is we're going to basically say that this point right here, we're going to call that the midpoint, and we're going to call it Q. How can we say that that's the midpoint? Well, we're drawing from what we call the midpoint postulate. The midpoint postulate states that every segment has exactly one midpoint. And so this segment is a line segment XY, has to have a midpoint. And let's designate that midpoint Q, which is exactly what we're doing here. Now, if that is indeed the midpoint, which we said it is, which we said that is the midpoint by the postulate, well, then that means that xq has to be congruent to qy, and therefore these two line segments are the same by the definition of the midpoint. And now that we know all these three pieces of information, we know that we have a side, angle, and a side for this triangle PXQ or XQP, and we also have a side, angle, side. And so we know that these two triangles are congruent. And so now that we know that they're congruent, we also know that by the CP/CTC, that angle XQP, which is this angle right here, has to be the same as, and let me go ahead and erase this just to kind of focus on the angle. So now that we know that those two triangles are congruent, then that means we know that this angle is the same as this angle. By the CP/CTC, the corresponding parts of congruent triangles are congruent. Remember that that states that if you know that two triangles are congruent, you can take any corresponding parts and set them congruent. All right, and so now we know that those two angles that we just mentioned are supplementary angles. How do we know that? Well, because these two angles right here, they form what we call a linear pair. A linear pair is formed when you have two lines that intersect. And then you have angles that are adjacent that are formed as a result of that. And therefore, these adjacent angles add up to 180, or they're supplementary. So that's the linear pair theorem. And so now we know, and because they're congruent and they're supplementary, so basically using these two steps here, we know that they have to be right angles because they can't be anything else, right? If these two are the same angle and they add to 180, well, then they both have to be 90. 90 plus 90 is 180, and they're the same number. And there's a theorem that we have discussed in chapter 1 that actually uses this. It's theorem 1-5, which states that two congruent supplementary angles are right angles. We'll show this right here. So this is the theorem from chapter 1. So if two angles are congruent and supplementary, then each is a right angle. All right, so we're referring to that theorem for this proof. All right, so now that we know we're using that theorem, let's go to step 10. We know that line segment PQ has to be perpendicular to line segment XY. Why is that? Well, because we now know that these are 90-degree angles, right? They're right angles. And therefore, since they're right angles, that means that this has to be perpendicular to this, just by definition. And now that we established that it's perpendicular, and we established that it cuts this in half, that means that by definition has to be a perpendicular bisector because it cuts it in 90 degrees and it cuts this in half. All right, so let's go ahead and apply the perpendicular bisector theorem with a couple examples. So we have, for this one, we want to find AD for the first example. So if we want to find AD, well, let's look at the type of proof here, or the type of problem that we're looking at. So we know that this is congruent to this, right? Because they're both have the same measure, which is 11 in this case. And we know that this is perpendicular because it's at a 90-degree angle. And so this has to be a perpendicular bisector because it's cutting this in half and it's a 90 degree. So first you got to establish what kind of problem you're dealing with. So this is definitely a perpendicular bisector. And by the theorem, that means that these two distances have to be the same. So basically you're dealing with an isosceles triangle. And so therefore these two sides have to be they have to be congruent, so those two measures have to be the same. And therefore, we know that 6x minus 10 equals 3x plus 2. Then we can solve that. So we're going to go ahead and subtract 3x on both sides. 6x minus 3x, we get 3x minus 10 equals positive 2. Go ahead and add 10 on both sides. So we had 3x equals 12, and then divide by 3. So x equals 4. So now that we got x, we can go ahead and substitute that in to find AD. So we're interested in this side right here. So we're going to plug 4 into this side. And so we know that AD equals 3 times x, which is now 4. Plus 2, so 3 times 4 plus 2, so AD is 14. All right, so let's look at the next problem. So we want to find OL, so we're interested in this part. So notice that there's two applications of this problem, right? We have these being congruent, and this is a perpendicular bisector because these two form an isosceles triangle. We know that that's the same distance, and therefore, by the converse of the perpendicular bisector theorem, that means that this distance has to be the same as this distance right here. And so I know that this has to be 14. And then we got another application of the perpendicular bisector theorem, the converse. We know that these two distances are the same, right? So here and here, and therefore, because of this perpendicular bisector, these two distances are the same. I'm going to use 4 tick marks there. And so therefore, if this whole thing is 14, then that means each of these must be 7. 7 and 7 give you 14, right? And so that means that OL has to be equal to 7.
All right, so what we are investigating here now is we're investigating bisectors of angles. So we're looking at angle bisectors here. So we want to investigate some properties of the bisector as it relates to like distances and stuff like that. So first off, let's review how to construct a bisector. We got an angle here, angle A. The vertex is A. The vertex is the common point between these two rays, right? We got these ray on the top, this ray on the bottom. So we're going to need to first draw an arc here just to identify 2 points on that on the different rays here, 1 point on each ray. So let's call this X and Y. And so now we got this angle XAY. All right. And I just arbitrarily called it X and Y. There's no real reason why I called it that. Other than I didn't want to use B and C because I'll use B and C later. So now what we want to do is putting our point here on X and Y. I'm going to adjust this. You can adjust this however way you want. Doesn't really matter. But keep the setting whenever you go to Y. So first draw an arc from X to the interior of this angle here. And then go to Y, keeping that same measurement. And again, another arc in the interior on the inside. And so now you see that those two arcs will cross. And now you can connect those with a straight edge. So we'll do that here. Okay, so that right there is my angle bisector, which is in this case a ray. And I'll call this point D. So this is ray AD. This is my angle bisector right here. So this is my angle bisector. And that means that this is cutting this angle in half. So this angle is the same as this angle. So that's what this is doing right here. And so what are some special properties of this? Well, if one of the theorem that we're looking into is that if we're a point on this bisector, let's say point D or any point on this here. In fact, let's do another point on this bisector, point P or something like that. Now, if I'm in this angle bisector, point P, then that must mean that the distance from each of the legs of this angle is going to be the same. So that means these two lengths are called sides here. So that means the distance from P to these two sides of the angle are the same. And the way we define distance here is we want the straightest possible path to that side. The straightest possible path here is a right angle. If I traveled here, then that's not going to really cut this at a right angle. That's going to cut it at a weird angle. Here, a weird angle, and it's a longer distance here. I want to go straight to it. So the shortest possible distance is going straight to it, which is technically speaking here a right angle. So we have here some kind of right angle, and that's the straightest possible path to that. And then we're going to do the same here, doing it at a right angle, the straightest possible path that we can. And of course, I didn't really measure this out, so I should probably, measure it out for this investigation, right? So if I were to do this, well, that looks like it kind of lines up with a 90-degree angle. It's not perfect, but it looks like it's almost 90 degrees if you were to line out there. And then here, you'd have to measure here to here, because you're measuring this angle right here. So you're measuring this angle. So this looks like it's going to hit, it's not quite 90 degrees. So let's fix that. So we want this to be almost exactly 90. So right here, oh, actually that's pretty good. That actually looks pretty close. So that's about 90 degrees. If you were to extend that line straight down, yeah, that's here at the 90. Okay, very good. That's pretty good for eyeballing it. So these are 90 degrees. Now, that means that this distance has to be the same as this distance. Okay, so that's what the theorem that we're investigating looks like. So here, this is 0.75, so almost 0.75 approximately. And then here, again, it's approximately 0.75 inches as well. All right, and so we know, so the theorem that we're investigating here is, if we are on the angle bisector, if we're on the angle bisector, then that must mean that the distance from that point on the bisector to each of the sides is going to be the same. All right, and that's the angle bisector theorem. And this works regardless where you're doing it, from whether you're at point D or point B. And we'll call these B and C. So that means PB is congruent to PC.
All right, so what we just went over was the angle bisector theorem. So let's go ahead and formalize it. So according to the theorem, if a point is on the bisector of an angle, then it is equidistant from the two sides of the angle. So here's that word equidistant again. And that just means, so if you're on a bisector, which we know that this is the bisector because these two angles are the same. And so by definition, this is a bisector. It cuts that angle into two equal angles. Then that means that you're equidistant from these two sides on this angle, which is at points B and C. So these two distances are the same. All right, so let's go ahead and prove the angle bisector theorem. So we're given that BAD is the same as CAD, so those are congruent. So that's given because it's a bisector. And we're also given that the distances that we're going from that point D to the sides are at a 90-degree angle. So that means that they're perpendicular, and hence why we use the perpendicular symbols. So we want to prove that BD is congruent to CD. So we're going to start with a two-column proof. We're going to start with what's given. The second step, we want to say, well, because they're perpendicular, that means that ABD, and so this angle and this angle, they're right angles, right? By definition, because perpendicular means that you're forming some right angles here. And then since they're right angles, that means that they must be congruent because they're equal to 90 degrees, right? All right angles are congruent. And so we know those two angles are congruent. All right. Now we're going to use the reflexive property of congruence because these two triangles share this side right here, AD. That means that AD must be congruent to itself. And so that's the reflexive property. So we'll say that this is equal. So we'll put a little tick mark there so that we can share that between both triangles. And so now we got an angle right here, and a side. So we got angle, angle, side. And that's actually one of our theorems to prove that those two triangles are congruent. And so we know that those two triangles must be congruent by AAS. All right, so now that we know that those two triangles are congruent by AAS, that means that I can set any two corresponding parts of the triangles to be congruent. And so we know that, now we know that BD has to be congruent to DC, and that's because we just established that the triangles were congruent, so those two sides have to be congruent by CPCTC. And now that we know that those are congruent, then we can just convert them to regular equal signs and eliminate the bars over them and say that BD equals CD. The distances are the same, and that's by the definition of congruence or congruent segments.
All right, so now we're going to investigate the opposite occurrence from what we did earlier. So now, this time, we're going to say, well, we have a point D in the interior of this angle, right? And we know that this distance is going to be the same from here to here. And let's go ahead and measure out that distance. Let's just suppose we have two right angles, and let's keep those distances the same, shall we? So we'll measure that distance. So we know it's going to be at some kind of at a right angle, right? So let's make sure that this is at a right angle. So this needs to be lined up here at this right angle. Okay, kind of like that. Okay, so go ahead and make that mark there. Okay, so this is the right angle here. And then we'll measure this. We know that we're going to try to make this a right angle. Choose around there. Okay. And so we know that this distance is the same as this distance. We'll measure it out just to be safe. Let's just assume that we know that that's the same distance. So a little over 1.1 1/8, and 1 1/8 inches. So 1.125 inches for both. So let's start with the assumption that we know that these distances are the same, and we just showed that they're the same. We proved that they're the same. We're showing that they're the same, but let's assume that we know that they're the same without even investigating into it. Then if these are the same, then that means that D has to be on the bisector of this angle A. So D is on some kind of bisector that cuts angle A in half. And so let's show this. So we're going to draw this line, and this line should be my bisector. So let's first draw that line, and let's use another color. Okay, so this blue is my bisector, and we want to show that this is the bisector, which means that we need to show that this angle here is the same as this angle. So that's a question mark right now. We need to figure that out. So let's investigate and look to see what that angle is. So if I were to line this up here with the vertex, and this angle looks to be almost 25 degrees, about 24 degrees right here. Almost 25 because it's almost halfway between 20 and 30. So this is about 24 degrees. And then if we measure this on the other side, we can rotate this and do it, but I'll do it this way just so that we can see it. And if we did that, and lo and behold, it's about 24 degrees right here. So this is the 25, this is the 24. So it's approximately 24 degrees. All right, and so now we know that upon further investigation, those two angles are the same, which means that this here is the angle bisector. This indeed is the angle bisector. And so we proved the opposite scenario. We were showing the opposite scenario, basically, we were investigating. If we knew that these were the same, these distances, then that means that this has to be on the bisector.
All right, so we're going to wrap this video up. We're going to, with a final example, we're not actually going to prove the converse of the perpendicular bisector theorem just for the sake of time here, because we've proven a lot of the theorems, but we're going to actually turn to an application. So we're going to use the theorems that we discussed, the most recent two. So first, looking at this first one, we're looking for KL. So we're looking for this length here, and we can tell that this is a bisector problem. This is actually this is not a perpendicular bisector. This should say angle bisector, but we can tell that this is an angle bisector problem because these two angles are the same, and so this is a bisector, right? So this right here is my bisector. Okay, so that means that since we're on the bisector, the distance from that point, which we call point L, to either of those sides have to be identical by the angle bisector theorem. And so I know that these two sides have to be the same. So this has to be congruent to this. So we got 2x plus 3 equals 4x minus 11. We can go ahead and solve for x here. Let's go ahead and subtract 2x on both sides. We had 3 equals 2x minus 11. We'll go ahead and add 11 on both sides. We get 14 equals 2x, divide by 2. So that means x has to be 7. So we got x is 7, and we're looking for KL, right? But we know KL is 2x plus 3. So we're going to plug this in here. And so we get KL equals 2 times 7, x is 7, plus 3. 2 times 7 is 14, so we got 14 plus 3, which means KL is 17. All right, which means that LM also has to be 17. All right, let's look at our next problem. We're looking for angle IGJ. So we know that, looking at this problem, we're looking for this here, I, G, and J. So we're looking for this angle. And we know that, we know these two. We know that this is perpendicular. And so this has to be a bisector, right? Because these two distances should be the same, then this has to be a bisector. This is the type of problem that we're dealing with. And they should give us this distance. So let's see if we can figure out this distance. Yeah, so in this problem, it didn't actually mention in this problem, but they should tell us, some of the sides, just like they told us some of the sides here. So in this problem, it mentions that HI is 7 and IJ is 7. So these two are 7. And it tells you that the angle GHI or HGI rather, is 25. Okay, so they're saying that this is 25 degrees and these are 7. Now, since we know that these are 7, that means that these two distances are the same. And if these two distances are the same, then we're going to be using the converse of the angle bisector theorem. So that means that if those are the same, that means that this is a bisector, which means that these two angles are the same. And so if this is 25, then this is 25. And so now we know that this is just a measure. So now we know that the measure of angle IGJ is 25 degrees. All right, that's going to do it for the video, guys. I hope you found this useful. And as usual, I'll see you in the next one.